Hello, can you hear me? Hello? Hello? Are you a student for Math 230? Hello? This should be a review session for exam 3 for Math 230. Well, nobody's here right now, so I guess I just wait a little bit, see if someone actually showed up, and then I'll start it. Or, anyone online, if you want to participate, you can just, you know, notify me that you are actually there, and we can start it right away. Hello? Yeah, anybody there? Well, nobody actually showed up in the room, so if there's someone online right now is watching, then just give me a heads up, and I'll start it right away. Okay, thank you. Well, I guess we can get started. If you have anything like, you know, you don't understand or you have any questions, you can, type your questions on the chat item or any. I don't know if you can use the microphone, but I don't think I can hear you guys. So, or just anything Okay, so let's start it. I believe this review session is for the upcoming exam 3, which contains the following sections, which are introduction to proofs and some proofs methodology or strategy, and the next chapter for sets operation, and functions, right? So the professor and I uh, trying to actually we did find out this some problems from the previous sample exams that actually based on those sections, and I can solve them for you right now. Well, we started from the first one. Actually, we have 5 sample exams, but not all the problems are relevant. We have to pick the things that are gonna be related to this exam. Well, the first one is number 12 here. Among a certain group of 27. This one. This is the first one. Among a certain group of 27 people, exactly 2 people are born on Sunday. Prove that at least 5 people were born on the same day of the week. Well, I don't know for other people, but I think this is a little confused. Well, what do you mean by on the same day of the week? Well, basically, after I read the solution, I think the question is asking something like this: if 2 guys are, born on Monday, and if they are both born on Monday, then they are they were born on the same day of the week. That's what it means. So we already know that exactly 2 people were born on Sunday, so we're trying to prove that out. At least 5 people were born on the same day. Really? You can't say anything? Oh, just give me a second. I'm not sure. How about now? Oh, okay, okay. My bad. I forgot to share the screen. Alright. Okay. Just anything else, just let me know, right? Uh, so now we're dealing with the number 12. You can read the problem. Among a certain group of 27 people, exactly 2 people were born on Sunday. Prove that at least 5 people were born on the same day of the week. And I just said what they mean by on the same day of the week. Oh, so basically we have to first, uh, you know, settle what strategy we have to use to prove this problem. So what do you guys think? How can we prove this question? Anyone? Just tell me what strategy can we use. Or maybe a hint for something. I know it's a little bit difficult if you want to hype a lot of things on board, but it just give me some like keywords or something. Okay, so if nobody have an idea, I'll just tell you how we can solve this problem. Well, we already know that for a week we have 7 days, right? A week. We have 7 days. Well, Monday, Tuesday, or sort of da da da, and finally we have Sunday. And we know that exactly 2 people were born on Sunday. That means all the other people are born on these 6 days. And we try to prove that at least 5 people were born on the same day. So now we can prove by assume the contrary. So our assumption is assume that on no day greater or equal to 5 people were born. Which equals to, the same thing as that on no day, okay. So it really means on each day that less than 5 people were born. And it really means smaller or equal to 4 people were born on each day. Is that correct? I'm not sure if you guys are still with me. Are you guys still with me? Okay. Alright, thank you. Well, now we know that our assumption is less or equal to 4 people were born on all the other 4 days. So the total number of people born on all days should be smaller or equal to 6 times 4 plus 2. Well, this represents those days from Monday to Saturday. And finally, this 2 is exactly 2 people were born on Sunday. So this gives us the total number of people to smaller or equal to 26. However, we have this group of people contains 27 people, which leads to a contradiction. That means our original claim is false, which means there are at least 5 people were born on the same day of the week. Is that clear? Oh, we have waiting for their response. Okay, so we can move on to the next problem. Okay, so next problem is number 13. You can read the problem first, and then we'll discuss how to prove it. Okay, so when n is an integer, the following are equivalent. That's our claim. We're trying to prove it. Well, if for a second we don't consider the problem first, how can we prove that 1, 2, 3 claims are actually true? we have to prove that the first and second are equivalent, the second and the third are equivalent. Or in this particular case, we can prove as, well, 1 leads to 2, and also 2 leads to 3, and finally 3 leads to 1. So that will prove that those 3 claims are actually equivalent. Okay, we can start from the first part. How can we prove that n squared is odd, then n plus 1 squared is even? We assume n squared is odd, so n squared can be written as 2k plus 1, while k is just some integer. Right? So n plus 1 squared equals to n squared plus 2n plus 1 equals to 2k plus 1 plus 2n plus 1, which is 2 times k plus n times 1. Okay, okay, so this gives us an even number. So that's how we prove that first leads to the second. Alright. Then we are trying to prove the second part. Which is if n plus 1 squared is even, then n is odd. We can use some technique here that we assume that n is even. We are trying to prove it in a counterpositive method. Right? So we assume that n is even. That really means we can written n as 2k, while k is just some integer. Right? And then we have n plus 1 squared equals to n squared plus 2n plus 1. Which is 4k squared plus 2n plus 1. And it is 2 times 2k squared plus n plus 1. Right.
So why can't you substitute the other one?
Okay, that's a very good point. Actually, we can do that, and it's better we do that. Thank you. It's 4k squared plus 4k plus 1. And it is 2 times 2k squared plus 2k plus 1. Right. So either way, we have n plus 1 squared is an odd number. So that gives us the opposite of the second claim, which means 2 leads to 3. Any questions? I'm talking to the ones online. Okay. Thank you. And finally, we have to prove that the third leads to the first. Well, I think you guys know where this is going. If n is odd, then we can write an n as 2k plus 1 and k is some integer. And then n squared becomes 2k plus 1 squared equals to 4k squared plus 4k plus 1, and equals to 2 times 2k squared plus 2k plus 1, which is odd number. So now we finished all three parts of this proof, which gave us a complete proof. No problem? Okay, let's move on. I mean, in an exam, you have this idea. I think you have to write more than what I just wrote to complete the proof. I mean, I just basically give you a hint or the way to prove it, but I didn't actually write down the proof like all of them. Okay. So number 14. Write down the power set of this set. What is the power set? Can anyone tell me here? What is the power set? Well, the power set is all the subsets of the set. Alright, so we know that for any set, empty set is a subset, right? Okay, so then a power set should start with an empty set. So start with an empty set. Well, then, because it contains all the subsets of the set, we have to contain all the elements. Well, here, empty set is an element, so we have to write in this way. And A is another element, which means this set is a subset of the original set. And finally, we have this set its own is also a subset. So this is the power set. And all the subsets of this set. Well, this problem is kind of tricky because it all has an empty set in it. So you have to make sure that you have empty set. Also, a set that contains only empty set. Okay. So now we move on to 15. Use Venn diagrams to justify the relationship. So we have three sets, I believe it's A, B, C. So in general, A, B, and C looks like this. So let's call this A, this B, this B, and this C. You can use different colors. Well, what is in this minus zero? No, just these dash. This part, right? Okay, and the B finally we have A, B, C. Well, A minus C minus B minus C, which gives us this middle part, right? This is A minus C. This is B minus C. Or this is A minus C minus B minus C. Okay. And finally we have the right hand side, which is A minus B. This is A, B, C. So N minus B is really this part. Right? So we can see very clearly that this little part is actually a subset of this. So we should write it as a subset. That's how we are. That's how we use Venn diagram to. I mean, it's not a proof, but just verify this relationship. All right. And then we move on to the last problem on this evening. Okay. We have to prove that right hand side equals to left hand side. And don't forget, a Venn diagram can be helpful, but it's not a proof. So we can now just draw some pictures and say it's a proof. It's really not. Because in general, A and B and C looks like this, but we don't know, like in particular, what are the things we like for A, B, and C. So it's not a proof, it's just some graph to help you understand this problem. Oops. How can we do it? Yes, we use the set method to do it. So there are three sets here. We have A, B, C. Alright? So what should I write like after? What should I write on? No, what should I write in this table? Okay, B intersection C. A union B intersection C. Okay. A union B. A union C. Yeah, and finally everything. Okay. So now we started this 7, which is table. I think it's not that hard, it's just like 2, 3, right? Okay. So 1, 1, 1, then okay, so it's 1, 1, 0, 1, 0, 1, 1, 0, 0, and well, let's just start with A is 1. So we have 1. Yes, of course, but
Okay,
There's
so you-
more here. I'll learn more later. It's 1, 0, 0, 0. And here we have considered this and this. So 1, 1, 1, 1. Okay, so A union B is 1, 1, 1, 1. A union C is 1, 1, 1. Finally, on the right hand side, we have the union of these two is really still 1, 1, 1. But don't forget where we should compare. We have to compare this column and this column, right? To see if they are always the same. Well, when when A is always, when A is 1, they are always the same. We can do the same thing with 0, and we can prove that actually they're equal. We need to write it down. Yeah, I can.
So you can write a really small.
Okay. So it's 0, 0, 0, 0. And 1, 1, 0, 0. And 1, 0, 1, 0.
Yep.
Okay. So 1, B and C, we have 1, 0, 0, 0. Okay? B and C are. So this is 1. So this is 1. The difference actually, so only 2, 1, 2, 2, 1, right? And for A union B intersection with C,
That, that's the all the two ones equal one, and this one is A and B.
so this is
But
B
here we
and
have
C.
this,
B and C. Because consider this
yeah.
one. So A union B and C give us is 1, 0, 0, 0. Okay, so for A union B we have 1, 1, 0, 0. And A union C we have 1, 0, 1, 0. And finally, A, these two, the union of these two will give us 1, 0, 0, 0, which is exactly the same here. So now we complete the proof that those two sets are actually the same. Any questions? Comments? Are you guys still with me? Well, you can find it afterwards online, so if you didn't really understand some part of it, you can just go back and maybe do it again. Okay. So now we can move on to the next exam. From this exam, only the last two problems are relevant. So write a complete and fully justified proof for the following statement. If x is an odd integer and y is an even integer, then x plus y is odd. I think this one's pretty simple. We can just prove directly, right? Okay. So we assume that x equals to 2k plus 1. Well, k is some integer. And y equals to 2k. Oh, sorry. We have to use another letter. We say 2l, but l is also another some integer. For here, we have to use different letters because we don't know they actually have the relationship, and we don't have any relationship. So now, for x plus y, we have x plus y equals to 2k plus 1 plus 2l equals to 2 times k plus l plus 1. And we have to say that k plus l is an integer. Do you know why? Yes, it's called a closure property. By closure property. And I need to, the sum of two integer will give us just another. So by definition, x plus y is odd. I think this one's pretty straightforward, so we can just move on. The second one, the last one is kind of tricky. Because we have to, first we can give you guys a little bit of time to read it. And we're going to use the same idea to prove that this equation has all the irrational solutions. Do you have any idea? Anybody with me here? Do you know, do you have any idea with this problem? Well, basically, I'm asking what kind of method can we use, or what strategy can we use here? Well, we have to prove that all solutions are irrational. So what is the strategy to do? Okay, first we can, assume the opposite. We assume that there is actually some rational. Then we prove that. Okay, so this is that strategy. But first, we can, justify one case that s equal to 0 is not a solution. So we can just plug it in, and we have 0 squared. Well, not equal to 0 plus 1, so 0 is not a solution. Or second, we can prove by assuming that there's some x. It goes to P over Q. Well, P and Q are all above non-zero integer, and they don't have, basically they are not divisible with each other. So we have e.g. GCD EQ is 1. Okay, so this gives us P and Q cannot be both even number, right? Right? So this give us 3 cases. For P is odd, or Q is odd. What about this? So P squared over Q squared equals to P Q plus 1. This is equivalent to P squared equals to Q times P plus Q, right? Compute this Q squared. Then if P is odd, I mean you have to write it down. Now just tell you. If P is odd, the P squared is odd, right? And if Q is odd, P plus Q is even. You can prove by, P equals to 2k plus 1 or Q equals to 2L plus 1. Then you can prove this properties. Well, then the right-hand side will give you an even number. Well, an odd number cannot equal to an odd number. An odd number cannot equal to an even number. So this case is false. Well, there are 2 other cases. Well, P is odd, while Q is even. And finally, P is even, and Q is odd. And you can by yourself that these two actually cannot happen either by using the same way. So we consider all the scenarios, and then they all cannot happen. So basically, we already know something is wrong, which means this equation really have all the irrational solutions. Okay, I think we can move on to the next one. There are only 2 problems in this exam are actually relevant. The third and the fourth. So for the third one, give an example for a function is a mapping from real number to real number that is 1 to 1 but not onto. Do you know what is 1 to 1? Okay. So can you give me
every number in the coded range has a number that actually is
yeah. Basically, that's right. Yeah. So I'll give an actual example. I didn't forget. Well, what is the function that has the property 1 to 1? Do you know what is the increasing function or decreasing function? Okay, so it's an increasing function by 1. Yeah, a monotonic function is 1 to 1. So for an example, we can automatically think of the increasing or decreasing function maybe 1 to 1. How about a function that is increasing but only, yeah, the only alternate side, like all the numbers for this function are only positive. No, that is not what I want. But what I'm thinking is y equals to e to the x. Okay? So for it's like this. It's increasing, so it's 1 to 1, but it's not onto because right, it's always greater than 0. Okay. So let's move on to the fourth problem. We define a function like that. So we have a composition of functions. We want to verify the values of those. So what is the value for the first one? First one. Yes. The first one is right half. Okay, what about the X. The unit of G and F.
Yeah, how would you do it?
Oh. Okay. So you can do it this way. I'm going to use some property. Or you can do it either way. Like what is the G of X? And you can see these two are one-to-one functions, right? This is increasing. This is also increasing. So the composition is also 1 to 1. And this gives us 2 to the x cubed. So if the inverse function equals to 16, then this equals to 16. Yeah.
When x is 16.
No, I'm asking, let's just call this network A. Okay, so the inverse function when it's 16 equals to A, then the original function when it equals to A, it will be 16. Right? You can solve for A here. So here 2 to the A cube equals to 16, so A cube is 4. So A is the cubic root of 4. You can only do it when it's 1 on 1. 1 to 1. Otherwise you can, or otherwise you will have a inverse function. So basically, or if you use this way, we have the F inverse G inverse 16. And for each one of them, you have inverse function because they are 1 to 1. It's log is 2 base 16. So it's F inverse 4, which is the same answer. Right? Okay, for this exam, sample exam, we have more problems than the first one. Suppose you need to give a proof that there is a unique number with a certain property. Which of the following is not a valid method of doing it? So for guys online, can you tell me which one? Or are you still with me? Okay, let's take a look one by one. Okay. So for A, prove that there is at least one number. So basically, what do we need for a proof where there's a unique number? Yes. So we have to prove the first thing is it exists, right? And second, prove there's only one. Right? So we have to prove this two parts. So proving that there is at least one number with the desired property, which gives us this, right? And there's at most one number. Is smaller or equal to 1, well, cannot be 0, it's greater than 0. So it's 1, only 1. So what about the second? Proving that there cannot be 2 or more numbers with the problem. It cannot be, so it's not greater or equal to 2. However, what if it doesn't exist? Right? So B is wrong. That's what we want. B. Let's consider C. Proving that there's a number x. So this means exists, right? And if y is a number with the desired property, then y equals to x, which gives us only 1. Right? And same thing here, B and E. First, proving that there exists a number, okay, exists, and there is at most one such number. So it's only 1. And proving there's a number with desired property, and if x not equal to x, y is not equal to x, y does not have a problem, which means this x is 0. Right? So B is 1. Be a little careful here. Okay, so the second problem is about the power set. I believe after what we did before, now we can easily do this problem. Just don't forget when something is a subset and something is element. This means a subset. This means an element. So what is the power set of S? What is the power set? Right. Okay.
These elements, 1, 2, 3, and 4, and then a subset that has just one subset, it's just 2, so it's just 3 and 4, and then every 2 of them, and then every 3 of them, and then have 4.
Yeah.
Oh, and here.
Empty set, right. So basically we're going to start with the empty set. And we have like just one element, right? And then 2 elements. Right? So then 3 elements, 4 elements. Okay. So now based on what we write here, we can justify like the first clip is in red. Is the first one right?
Okay, it's not right because it has 2 different images, but I'm not sure why.
Well, you see here, this one with a bracket element. So if for a set that contains this element, it's like this. So it really means this set contains a set. And this set is the element of the polyset. So we know that this element is this set is the element of this whole set. So the set containing the set really is a set of all the sets. So what about the second and third? Why? Is it?
Or does it have to be the set that contains this one?
Yes. It should be like this, then it is right. Well, otherwise, the third is right because this is the element. So we use this little sign, right? Okay. So now for the first one, is it right? Yes. Because it's a set that contains two elements in this power set. Okay, finally, what about the fifth? It's not right. Okay, this is just an element we have to use. Okay, so you can summarize the answer to 1, 3, and 4. So it is C, right? It's C is right. Okay. So we can move on to the next problem. Okay. You can read the third problem. Which one of these rules define a function? Is the second one right? Yes, because this is not in that set, right? There are not numbers, so this is wrong. What about the first one? Yes, this is a function, and we're going to see why the others are not. The first C, the rules assign string of the members of volume in the string. For example, yeah, it can be 0 and 0 is not in that. Okay. And what about C? Yeah, the number of Z can be 0 as well. And finally, the last one. Well, so the question should be asked is what if there's no Z here, right?
Oh, yeah. I thought they like mean that they're like
Yeah.
represented by C.
Oh no.
No, they mean the letter C.
Yeah, the first C,
Oh,
right.
okay.
Okay. So what if there's no Z here is 0? Then only the A part is right. Okay, number 5. The A to B is a function. Which one of the statement is true? Let's just take a look. Right, you said B. If A1 and A2 are distinct elements of A, just what is the answer of the number 4? Okay. Oh, we are not talking about number 4. This is something that won't be the end. Oh, okay, number 3. Number 3, it should be A. That's alright. That's alright. A is correct, and then all the others are wrong, right? Okay, so if A1 and A2 are distinct elements of A, then FA1 not equal to FA2. So what if fx equals to x squared? Is it not? Okay, so A1 is negative. A2, yeah, is 2. There are 2 distinct elements of A. Well, FA1. So we know that this is another thing. Any other evidence?
Can we go to the chat?
Right. Okay. So for the first one, if B, small b is in the set B, you take B. Okay. Well, B is actually correct. So, well, for the first part, if B is some element in the set B, there is at least one element A such that f of A equals to B. That is not true, right? There can be some element that can be left out for the set B. So A is not true. What about C? If B, B is the element of set B, there is exactly one A such that, if A is not true, C is not true either. Because, there can be even doesn't match the B. Then finally, for each element A, there is exactly one element B such that. Okay, so we know that B is right. Now we move on to the sixth one. Suppose you want to prove that the following is true, for all pairs of distinct real numbers x and y. The average of x and y lies between x and y. Which of the following can you assume without loss of general knowledge? What? B? What is a real number? For all pair of distinct real numbers x and y. Okay. Right. The A is right. Because if x smaller than y or even x greater than y, then it really doesn't matter. But we can say if x and y are integers or even numbers. Also, we cannot say x is smaller than 0 or y greater than 0. Because that will make the region we prove smaller. We want to prove a more general thing. Okay, we can move on to the 8. Oops. Good. Okay, let's take a look at the 8. Oops, sorry. Do you know what the De-Morgan? What is De-Morgan's parameter?
I don't know. It's studying.
Okay, for De-Morgan's rule, we use S and T. If you use S and T, we have to So, by the Morgan's rule, we know that C is automatically and B is right. Right? So here if you use the complement here, then we have another complement which really is unity. Right? So that's how we can prove that B is right. And for A and D, for A, we can use the set membership table, right? So if S is 1, T is 0, then it's 1, 1 will give us 1. And here we have 0, 0 will give us 0. So they're not all and we can do the same thing for D. Well, D is kind of complicated. So we can still use the set membership table S like this. Well, S minus T is really S intersect with T coverage, right? And we T intersect S. So we use the stat membership table. We're gonna verify this is not true in general. And we use the only one. So okay. So we take a look at the 12. Prove or disprove the following. Well, in this exam, you got some partial credit for, way that way. But it's not a proof. Because, again, you can also. Yes, you can do that. You can definitely do that. Okay, so, but how can we use the stat membership table here? If this, can we start with this? Right, we have to start with A and B. So, I mean, we can use the stat membership table, but you have to use some more words to understand.
You could say that in all of the rows when
Yes.
equal and
Uh-huh.
and
Right. That is the way to go. Or maybe if you want to save some words, we can prove by counterplot. Okay? So if A not equal to B, so whatever. So what if that A is not equal
B.
to Right, but how can we prove that? Okay. So if A is not equal to B, then it's gonna be two cases. Well, the first one is if there's an X is an element of A, well, X is not an element of B, then that will give us A is not equal to B, right? Then X will be in A union B because X is in A. Well, X is not in A intersection B. So this gives us A union B is not A intersection. Okay? And also there's another case. Well, if Y is in B, well, Y is not in A. It's all the same thing. So either way, we have if A is not equal to B, then the intercept of those two is not equal to the union. Okay. So finally, we can move on to the next problem. Okay. So in this exam, you can choose whether you choose, but as a practice, I suggest you prove exactly one of the following two statements, clearly identifying which one you select. Okay, so if you want to prove that these three statements are equivalent, you have to prove that A is equivalent to B and B is equivalent to C. Right? So how can we prove that? Or can we take a shortcut and only prove some one? Well, in this one, we have here, it's kind of hard to prove if B and C. We can just prove if A then C, or actually it's A equivalent to C, A equivalent to B. They will help me prove. And I think after the example from previous exam, we know how to prove. So let's move on to the second one. The equation, well, 2x squared plus y squared equals 14 has no positive integer solution. How can we prove this one? Any ideas? But how can we prove this one? Has no positive integer solution. Is x, y positive or negative even matter? I mean, we have to take the squares, right? So, well, let's just say if there's any solutions, all right? Is there any restrictions for them? Well, we know x squared is greater or equal to 0, right? And y squared is greater or equal to 0. So let's just say can x equal to 100 be a solution? Why? No, I'm just asking if x equal to 100 can be a solution. Is it possible? Right. We can think that this is the right thing. The reason why I'm asking if x equal to 100 is possible to be a solution is that we already have x squared greater than x squared greater than equal to 0 and y squared greater than equal to 0. So if x equals to 100, 2x squared will greater equal to 14. Right? Actually, it's greater than 14. So y squared was smaller than 0, which is impossible. So there's a bound for x and y. And what is the bound? Well, don't forget they have to be here. So okay. So for x and y, well, we can start with positive integer solution. So we can start with 1, right? 1 and 1 is that. Right? We can just verify each case. Okay, so it's 1 and 2. It's not right. And y and 3. Y and 4. I mean, y and 4 is impossible because 4 squared is already greater than 14. So, for 1, 2, 3, it's not working. And what about x equals to 2? 2, 1 works? No, right? So 2, 2. With the 2 times 2 squared plus 2 squared equals to, yes, 12. And 2, 3 is 2 times 2 squared plus 3 squared is greater than 14. That works. And finally, we have if x equals to 3. It's already greater than 14. So these are all the scenarios that could happen. Well, fail to be the solution. So we know that there's no combination. Well, basically, we list all the cases that can be the solution and verify if it can be. Well, all of them failed. So that's how we prove that there's no combination. Okay. Let's move on to the last exam. Okay. Oh, well, actually, we don't have to prove B to C from B to C. Well, if you want, you can, but you don't have to. Well, the strategy for this problem is to prove A are equivalent to B and A equivalent to C. We don't have to prove B and C are equivalent. But however, if you really want to prove, you can always prove it. Like, if n squared plus 1 is odd, then the n cubed is even, right? And n has to be even. Yeah. And if n is even, then n squared is even, and n squared minus 1 is odd. This is not a formal proof, but this gives you an idea, right? Okay, so, but we don't have to do this. We can use only A and B and A and C to prove it. It's much easier. Okay, let's move on to the final exam. Well, this is actually the final exam for 2009. Okay. Okay. So let's consider the second problem. We are trying to prove that n plus 1 equals to n plus 2. What is wrong with the following proof? Just read how we prove it and see why it is wrong. Winston, oh, can you guess? Do you know what is the mathematically done? Well, it says, if pk is true for some positive integer k, then k plus 1 is also true. Well, we have to, just go back to check. We have to have a basic set that when k goes to 1, it is true. Then, if we have, for any k, we have k plus 1, this will otherwise it will give us some obvious wrong statement, right? This is nothing wrong with this proof, well, obviously n plus 1 is not n plus 2. Alright, what about the third one? Well, which of the following is a set as equals to the set of positive integers not divisible by 3? C, right? Yeah, C is actually right. But why the others are wrong? Yeah, for all the integers that are not divisible by 3, it's like 1, 2, and then plus 3, right? So C is exactly this way. 1 is in the set, 2 is in the set. And for all the x in the set, here we have 1 and 2, then x plus 3 is in the set. So basically 1 is in the set, 2 is in the set, and all the after 2 plus 3 is in the set. But for, let's just say for A, 1 is in the set, but 2x plus 2, whenever there's an x in the set, 2x plus 2 is in the set. Well, if 1 is in the set, then the next one is going to be 4, while 2 is not in the set. So A is not complete. And if 1 is in the set, x to x plus 1, x plus 3 is in the set, 2 is also left over. And finally, here, 2 is also left over. So C is the only one that is correct. Okay, let's consider number 6. If the product of two integers is even, then their sum is also even. Circle the letter of correct assertion. Sure.
I don't know. Yeah, I'm gonna go back and study what the definition.
Okay. Okay, so if the product of two integers is even, then their sum is also even.
Thank you.
Is it true or false? Yes. But why? Okay. So we settled A is right. We can find a counterexample, but what is a counterexample? Yes, that will work. Actually, we only have to find an integer that is even, the other one is odd. Then their product is even, and also their sum is even. Oh wait, that is not true. Their sum is also even. Yes, yes, that would do it, right? If integer is even and the other one is odd. Well, their product is even while their sum is odd. So that's why how can we prove by a counterexample? Let us move on to the eighth one. Or suppose, this function is 1 over x cubed minus x. Which one can be the domain? Well, when is not the case for a domain? It's something like 1 over 0, right? Yeah, the D is right. Well, is when x cubed minus x equal to 0, x times, well, you can factor out the x. So x cubed minus 1 equals to x times x minus 1 plus x plus 1 equals 0. So there are three cases, x equal to 0, x equal to 1, and x equal to negative 1. So we have to rule out those three numbers, that give us D. Okay. So the next one is the ninth one. Suppose you want to prove that the square of every even positive integer ends in 0, 4, and 6. Which one is the strategy to prove this? Yes, prove by cases, but what are the cases? Because for even positive integer can only end up with 0, 2, 4, 6, or 8, right? And 0 squared will give us 0, 2 squared will give us 4, 4 squared will give us 6, 6 squared give us 6, and 8 give us 4. So that's all the cases that could be for even positive integer. That's how we prove by cases. Okay, that's great. And let's consider the 10th one. Suppose you are examining a conjecture of the for, for all x, p of x leads to q of x. Well, you can, but first of all, well, in this problem, you only have to find a counterexample. That's all. So what could be a counterexample? Well, you can definitely do that, but well, in this problem, just ask for a counterexample. So what could it be? Yes, it is EV. Well, for a counterexample, just for some x, there exists x such that we have p of x, but not lead to q of x. Basically, is p of x will leads to not q of x, right? So p of x is true while q of x is false. That will be it. There. Okay, we can consider the 11th. Are you familiar with the notation for this? It is called the greatest integer function. It's just the greatest integer that is smaller or equal to the number in the bracket. So if, say, 3.1, this will give us 3. And 4.9, it will still give us 4. And if inside the bracket is the integer itself, it will give us itself. Like for 5, it will give us 5. Alright? So now we consider this composition function. Okay, so which one of this is right? Or you think is right? Hello, are you still with me? Oh, it's -1. Yes, it is. It is right. It is -1. So if you want to find the solution, you give us uh, fg of y, right? And this is f 5 minus 2 times 5. Oops. Oh, right here. Anyway. So it's 5 fg of y, which is f greater integer, which is f negative third, which is f -1, right? So it's the integer of -1/2. You give us -1. So it is -1. Alright. So let's move on to the 12th problem. So 12. Let f this function. Well, we have the corresponding a and b, the set for domain. Which one do you think? Yes, it is b. We have if x equal to -3 is 9. This is 4, so 1, 0, 1, and 4. So in the set B, those are all the possible numbers for f of x if x in the domain of A. That will make this function onto. Well, for others, either they are I don't know where this comes from. They're not possible. Well, for some of them, and for this one also, and for this one, there will be some of the values of the function that are not in the set. So that will make this function not an onto. Okay, so B is right. Okay, so we can move on to the final problem, 18. Well, this is the last problem. Well, there are some others, but they are just very similar to what we deal with before. So I think this is the last problem that we need to consider. Okay, so which one is true? Well, maybe, well, always true for set S and T. Yes, B is right. Well, for others, they are not look like right because as union T, wait a minute. Oh, right. So here is belonging to, not a subset. So that's the problem, right? And of course, this will not hold for all s and t. And also this. I mean, what if the intersection are not empty set? And finally, this cannot be true, like always, right? And for this, we have x union t complement intersect with t union s complement. Basically, t complement and t cannot have intersection, and also s and s complement cannot have intersection. That really means this will always be an empty set. Okay, that's all. Well, is there any other problems or questions regarding this upcoming exam? Yes, actually. Well, I don't think other people are participating. Or, oh, actually, your classmate didn't really agree. Somebody else is there. Yeah. Okay. Well, I hope this is helpful. No problem. No problem. I mean, if you still have questions about this exam, I think it's on Thursday. So before that, you can either talk to your professor or go to the ARC. You know where that is, right? You can ask for a tutor for help. Okay. Give an example of a function R to R that is strictly increasing but not onto. I mean, that should be considered. I mean, that problem. But we just did a problem like that. We just did a problem for gave an example of a function that from R to R that is one to one but not onto. Like I said, for one to one, most of one to one function or increasing or decreasing, or in general we call it monotonic. And so that example will still work. Like y equals to e to the x. Can you verify if that is an example of that? Not really? Why not? You're not sure. Oh, okay. Well, it is strictly increasing, right? Is this strictly increasing? Okay. But y is not onto. Can this function be negative? When it's not onto, when it is onto, that for all the codomain R, there is a corresponding element that is in the domain to associate with it. Well, you can go back to check the book and find out the definition for onto function, and you'll see that we have to make every element in a letter R that has a corresponding element in the domain. Well, for y equals to e to the x, this function cannot have negative values. That really means it cannot be from R to R. It's from R to R plus. All right? Any other questions? Okay. That's great. Is there any other questions? What do you mean long questions? Well, in this exam, I believe the last two problems are relevant, but we already did that before. They are not exactly the same, but are very similar to what we did in the previous sample exam. Okay, let's just say for 32, right? Is exactly like the case for 2x squared plus y squared smaller equal to 14. Well, actually, this is exactly the same because you just multiply by 2 for each term. And for 31, you can use the set membership table. It will work out immediately. Okay, so there's no more questions, I believe. All right. Well, thank you. Yeah, have a good night yourself, and good luck on the test.